Hello, and welcome to the Space Telescope Public Lecture Series. Tonight, First Light, Hunting for Galaxies at the Dawn of Cosmic Time by Dr. Guido Roberts-Borsani of UCLA. I'm your host, Dr. Frank Summers of the Office of Public Outreach here at the Space Telescope Science Institute. And as always, I want to thank our wonderful tech team, Thomas Marufu and Grant Justice. I also need to continue to remind you that we will be online only until further notice. Our upcoming talks on October 4th, The Universe of Dante Alighieri by a descendant of Dante Alighieri, Spirello di Sorrego Alighieri. This should be a massively interesting talk. I'm really looking forward to it. On November 1st, Black Holes. How do we see that which gives off no light? From Stephanie Lamassa of the Space Telescope Science Institute. And on December 6th, High Energy Astronomy with the Swift Observatory by Stephen Kirby at Penn State University. We talk a lot of our space telescopes. We have not yet had a talk from someone about the Swift Observatory, so this should be a treat. All this information is available on our website, www.stsci.edu/public-lectures, which will give you this webpage you see here in front of you. On the left side, you can see our webcasts, both our YouTube playlists and our webcast archive at Space Telescope Science Institute. And on the right, we have the box where you can enter your email address and subscribe to our email list. Also on that page are the list of the upcoming lectures. And if you click on one of those lectures, it will give you all the information about it, including the description of the talk. And after it has been presented, we have the STSCI webcast link. And down at the bottom, you can see the YouTube webcast link. Our email is basically twice a month. You get a reminder of things. You can sign up at the website as I showed you. And in addition, you can subscribe to our YouTube channel, youtube.com/Hubble Space Telescope, all one word. You will get the notices of new videos that we post on our channel and reminders of live events such as this. Finally, if you have comments or questions, you can send them to the email address publiclecture@stsci.edu. Our social media for the Hubble Space Telescope, the James Webb Space Telescope, and for the Space Telescope Science Institute is available on Facebook, Twitter, YouTube, and Instagram. I myself do a pathetically tiny nothing's worth of social media on Facebook and Twitter as Dr. Frank Summers. And now the news from the universe for September 2022. Our first story, Betelgeuse blowout. And if you are a regular viewer, you remember that Betelgeuse has been spoken of just a bit over the last couple of years. First of all, let me remind you that Betelgeuse is one of the very, very, very few stars that can actually be resolved. It is the left shoulder of Orion, in the constellation Orion. The left shoulder is Betelgeuse. And Hubble, here in 1994, did an observation where it resolved that star as more than just a point of light. It actually resolved the disk of Betelgeuse. Betelgeuse is a red supergiant star. And if it were in place of our sun, its atmosphere would extend out past the orbit of Jupiter. Okay, that's how huge it is. And that's why Hubble can actually resolve the disk of the star, right? But what the recent thing is that in 2019, Betelgeuse dimmed unusually. Right, so this is two observations of Betelgeuse, one from 2016 and one from 2019, and you can see how much dimmer it is in 2019. Betelgeuse regularly fluctuates up and down just a little bit, but now it was at 40% of its regular brightness, which is a significant dip in its brightness. However, when that happened, Betelgeuse did not change its general characteristics. So this is a spectrum of Betelgeuse. The red line is from 2004, and the black line is from 2020. And you can see that the dips and wiggles in this spectrum, all of the absorption lines and emission features are this same. It's just that in 2020, they're at a lower level. So it's the light from Betelgeuse that has dimmed. It is not the character, essential character of the light that is actually changing. So that led us to believe that instead of a major change in the star Betelgeuse, really that there was a cloud blocking it. So the story we developed based upon the observations is that in 2019, there was a blowout from Betelgeuse. Probably a convective cell about 1 million miles across erupted through and blew out into space in the direction towards Earth. That material then cooled and turned into a dust cloud that blocked some of the light. So from our point of view, we were seeing Betelgeuse with this dark, dusty cloud in front of it, which blocked a lot of its light and dimmed the star Betelgeuse. But the star itself was not, did not suffer anything major. All right, and then it has since recovered. And so you have to understand that, as I said, Betelgeuse is a variable star, and it regularly goes up and down in its brightness over a small range over a 400-day period, okay? So this sine wave here is to represent the 400-day brightness period. Relative to that, here in red are the actual observations. So you can see that in the left side here, it's following its dip down and rise back up. And then the explosion happens, and then it dips way down, okay? This is down around 40% of its brightness. So it's several magnitudes too faint. And then it rises back up as that cloud dissipates. So it's now back up at its roughly average brightness, but it hasn't fully recovered from this eruption, because you can see it has not fully gone back into that standard 400-day brightness period change, this 400-day variability. And the 400-day variability is something that has been observed on Betelgeuse for centuries. Okay, so it's not a short-term effect. This is a long-term thing. So it did have a blowout in 2019, 2020, and it has returned back to normal, but not quite fully normal. It doesn't have its long-term variability period reestablished yet. We will continue to keep watching to see how that goes. Second story, turning cartwheels in the sky. And I'm referring to the famous cartwheel galaxy. And so this was resembling, not the cartwheel that the kids do when they turn over in gymnastics, but really the wheel of a cart, where you have the central hub, and then you have the wheel around it here in this galaxy. This is what's known as a ring galaxy, and is believed to have been caused by a smaller galaxy popping right through the center, creating a ripple effect that spreads across and created this ring here. You can see it has two companion galaxies here on the left. Neither one of them is believed to have been the small galaxy that popped through. There's a third one that they call G3 that's off screen that is believed to be the one that created the ring structure. But it's a very beautiful structure here. But this image from Hubble was taken back in 1994 with Wide Field Planetary Camera 2. Well, even by Hubble standards, it's a kind of crappy little image, okay? It's 600 pixels by 500 pixels. You can see that in the galaxies, They're a little blown out, this galaxy here. Its core is totally blown out. You can't see any details here. The center of the cartwheel is blown out. So by today's observational standards and image processing standards, this is not a great image. However, we have just observed this with the Webb Space Telescope, and Webb gets a much better image. Yeah, much, much better, okay? The Webb image is 4,000 by 4,000 pixels, much, much higher resolution, and is using a brand new detector that is up there. So there's your Hubble, visible light, and there is Webb in infrared. Amazing sorts of details, and like most of the Webb images I've seen, some of the coolest stuff is not the foreground. Say, oh yeah, the Cartwheel galaxy is cool, and these two galaxies are cool, but look at all these background galaxies. All right, that's just fantastic detail in the background. Most every Webb image I've seen has this, simply because the distant galaxies are redshifted a little bit, and they show up better in infrared light. So you get not only the sensitivity of the Webb detectors, but you also get the advantage of looking in infrared, and that pulls out those background galaxies. But there's one thing I'd like to express to you a little bit more deeply about this, because this is a combination of near infrared imagery and mid infrared imagery. Let me explain a little bit, okay? So here is the wavelength from 0.1 micron all the way up to 100 micron. And that covers from the ultraviolet through the optical to the near infrared, the mid infrared, and all the way to the far infrared. You know, while optical covers just a small range of wavelengths, you know, about 400 to 700 nanometers, or 0.4 to 0.7 microns here, infrared covers a factor of over 100, from less than 1 micron on up to 100 microns, okay? So there's a lot larger in factors of wavelength change in the infrared, such that we talk about the near infrared, the part of the infrared that's nearest to the optical, and then the mid infrared. And JWST, as you can see, covers both the near infrared and the mid infrared. And because these are widely separated in, from 1 to 10, you can get a factor of 10 in wavelength difference, they actually see different things. And I just wanted to illustrate that with you with the Cartwheel galaxy, because we not only released the Cartwheel galaxy with this combination near infrared and mid infrared, we also put it on our website in just the near infrared. Okay, so if I go back to the combo image and then I go to the near infrared, what do you see? All that red, the mid infrared was colored red in the previous images, goes away. All right, and the gaseous structures that you see in the main Cartwheel galaxy and one of the small companions go away. And what you're really left with is stars. The near infrared is great for seeing the stellar structures, right? So if I go to the mid-infrared, here's the mid-infrared image, and you get that gaseous structure back, but you lose the stars. Look at this small galaxy here, right? If I go back to the near-infrared, you see lots and lots of stars around it. Not so in the mid-infrared. The mid-infrared does not see stars very well, but it does see the gas. So if I take for this and I go to the combo image, you can see that that red that's there, all that gas and dust structure in those two galaxies, is what you see in the mid-infrared. So what you really want to do when you're understanding these images is recognizing that the near-infrared and the mid-infrared can see totally different structures in them, all right? The near-infrared is the instrument, it's called NIRCam, and that's wavelengths from 1 to 5 microns, and it sees the stars better than the other ones, and it will be at a higher resolution, okay? This will be getting the 4,000 by 4,000 per image resolution. The mid-infrared, which is the MIRI instrument, goes generally from 5 to 20 microns. It sees the gas and dust better. The gas and dust emit better in those wavelengths, but it is of lower resolution. And that's not due to any fault of MIRI. It's just the fact that to gain resolution is determined by the size of your mirror to the size of the wavelengths. And so for longer wavelengths, the same mirror will only give you less resolution. So by going up by a factor of 5 or 10 in the wavelengths that you're observing, you're going to get that correspondingly less resolution. So the MIRI instrument has less resolution than the NIRCam instrument. But it's something to look out for in the James Webb images as they are released, because you get to see two different sides of the same object, as well as we will generally produce a combined image that gives you both of them together. And now back to our featured presentation. Guido Roberts-Borsani is out at UCLA in Los Angeles, but he is originally from the UK. He did his undergraduate degree at the University of Kent, although he did come to the States there. I guess he maybe developed a love for California. He has spent a year at University of California, San Diego, but he was back in London, University College London, to do his PhD. And then he came to UCLA, where he's been a postdoc there for the past 3 years. His main research, well, that's what he's going to talk to you about, looking for galaxies at the dawn of cosmic time. But he is also involved in one of the early release science observations for the Webb Space Telescope, the GLASS project. And so you'll probably be hearing from him or his team again in the near future with their results from that. In his spare time, he's very athletic. He grew up playing soccer and doing all sorts of sports. He's a surfer there in California. He loves to go hiking, which is another great thing to do in California. So I'm not sure he's ever really going to want to leave California because he's got such great sports available to him. He might have to. But until then, we're happy to have him here. Ladies and gentlemen, Dr. Guido Roberts-Borsani.
Well, thank you very much, Frank, for that wonderful introduction. It's my great pleasure to chat to you today. Let me just share my screen over here. There we go. So it's my great pleasure to chat to you today. I'd like to thank the organizers for giving me the opportunity to talk a little bit about the research that I'm doing over here at UCLA. It's a particularly exciting time with the arrival of the James Webb Space Telescope. And in particular, what I'd like to do is take you right to the very edge of the observable universe. And together we're going to go through a journey through about 96% of cosmic time, right to the very beginning of when the first stars and the first galaxies formed. And what I'm going to talk to you about today is hopefully give you a little bit of a description of how we search for these galaxies, why they're important, and also how we've been using our foremost telescopes to really push the boundaries in terms of characterizing their properties. And finally, I'll try and end with a little bit of showcasing, let's say, of the very first data that we've obtained with the James Webb Space Telescope, and how that telescope is well, revolutionizing early galaxy evolution already. So to start off with, as astronomers, our aim really is to try and paint a coherent picture of the buildup of matter in the universe. And through the eyes of our foremost telescopes, we essentially can directly witness the past. And what I mean by this is, if you look on the left side of this screen, for instance, you can see two very large galaxies, one at the top, which is a spiral galaxy, one at the bottom, which is what we call an elliptical galaxy, essentially just a sphere of a few stars. It's not really forming many stars anymore. It doesn't seem to have this beautiful ring-like structure that this Milky Way-like star-forming galaxy at the top does. And these two galaxies exist at the present day, so 13.8 billion years after the Big Bang. But if you just go a little bit further back to about 6 billion years after the Big Bang, you can see that these galaxies look very, very different. So we've crossed a large fraction of cosmic time, and you can see the galaxy at the top looks rather different to what we see on the left, but it might be a precursor to this spiral galaxy, whilst the galaxies at the bottom might be precursors to the elliptical galaxies. So I'm sure you'll agree they already look quite different, but there seems to be a little bit of resemblance in terms of the structures. On the right, however, if we look even further back in time, so now we're crossing about 96% of cosmic time or so, about 1 billion years after the Big Bang, you can see that these galaxies now lose all resemblance really to the galaxies that we see in the present day. You don't see any more lovely spiral arms, you don't see any more real structure, they're pretty much just these small blobs. And this red that you see from the galaxies is not how they actually are. If we were to travel to them, they wouldn't be red. This is just an artifact of how we image them. So why is it important for us to paint this picture of cosmic history? It's good, I think, to put this into context a little bit. So over here, you can see the history of the universe in graphic form with the age of the universe there at the bottom. So on the left, you have the Big Bang, which we're all familiar with, about 13.8 billion years ago, at time, universal time equals 0. Straight after that, you have this beautiful imprint called the cosmic microwave background, which we image with WMAP and also the Planck satellites. And this imprint is the imprint of the Big Bang. This is what we see and is characteristic of the large scale structure that we see today. It's the seeds for that. Straight after that, we enter a period called the cosmic dark ages. Over there, this sort of dark stripe right in the middle over here. There is a complete absence of UV sources. There are no stars, there are no galaxies. All that exists for the time being are clouds of atomic hydrogen. So let's call it a fog, essentially, of cosmic hydrogen. But then approximately 1 billion years after the Big Bang, the very first sources start to form, the very first UV stars. These stars then merge into globular clusters, and these clusters then start forming the very small first galaxies that you saw in the previous image. And crucially, these galaxies start emitting a lot of UV light. And this is important because this UV light ends up stripping the electron from the proton, i.e. the hydrogen atom, and ionizes the universe into what we see today. So you can see the very first sources start to form over here. Then through gravity, they combine into bigger and bigger structures. They put these ionized bubbles, which you can see around them, start to percolate to create bigger and bigger bubbles. And then eventually all of this neutral hydrogen fog is ionized, and you see the beautiful structure, both in terms of the universe and also within the galaxies themselves that we see today. So clearly the emergence of the first galaxies and the first stars is extremely important for how it impacted the universe into what we see today. And this epoch is called the Epoch of Reionization. And this is going to form the basis for my talk today. And if we were to take a slice of the universe at this particular time, it might look something like this. This is a small little video where you see essentially a sort of block of cheese, let's say, in terms of the universe, and the dark clouds are this neutral hydrogen fog. So this hydrogen is blocking the UV light of the galaxies. It's absorbing it and it's essentially getting burnt, let's say. You can see those sources in the middle over there, these yellow dots, and you can see these bubbles getting bigger and bigger as time goes on, until eventually all of that hydrogen is burnt away and we get the universe as we see it today. So we want to characterize then these distant galaxies because clearly they had a profound effect on the universe as we see it today. But what does that mean exactly? When we say characterize a galaxy, what does that mean? Well, I think it's useful to try and understand a galaxy's composition. What does a galaxy actually look like? So this is an example galaxy in the local universe, and you can see that it has quite a few components to it. It has some stars, both young and old. It has dust over here. It's also got gas, hydrogen gas, for instance, or gas from metals. It also has a supermassive black hole right at the center, which is this particularly luminous point. And all of these things combine to give a particular light profile to the galaxy. So that's what you're seeing over here. This black curve essentially is the total light profile of a galaxy as a function of wavelength or frequency, shall we say. And on the y-axis, you can see it, the brightness of that profile. So you see the brightness at different wavelengths really changes, and that's due to the composition of the galaxy. You can see the individual contributions from young stars in blue over here in the ultraviolet. When you start getting to the rest frame optical portion of the spectrum, you can see old star contributions in red. Whilst underneath that, you can also get the contributions from the gas that's in the galaxy. Let's say, for instance, hydrogen or carbon or oxygen. And these create these peaks over here, these emission lines. And so overall, that then creates this black profile that you see here. But if we were to point our telescopes at a particular wavelength, sort of blindly, let's say, trying to look at this portion of the galaxy spectrum, we might be disappointed. The reason for that is the effect that we call redshift, the stretching of the universe. So this is an example. You have the Earth over here, you have the galaxy here in the middle, which reside in space. And as the universe expands from the Big Bang up until now, you can see that it ends up stretching the space between the Earth and the galaxy. And what this does is it stretches the spectrum to redder and redder wavelengths. That is why the galaxy appears redder and redder the further away it is from Earth. And this is particularly important because it means if we are to look at the galaxy, let's play that one more time, in the ultraviolet, for instance, we would see it if it's close by, but we might miss it when it's further away because the galaxy is no longer emitting light in the ultraviolet, it's emitting it in the infrared. And that's nicely highlighted in this schematic below, where you can see that as redshift increases, so the distance between the Earth and the object, the number that characterizes the stretching of the universe, the light of the galaxy then shifts from the visible or the ultraviolet into the infrared. But this is actually sort of useful because it's allowed us to develop quite a useful technique to try and confirm the distances to these very distant galaxies, or the redshift. Redshift and distance essentially equals sort of more or less the same thing. They're proxy for the two. So this is called the Lyman break technique. This was pioneered by Chuck Steidel at Caltech in the 90s. And here at the top, you can see again the light profile of a galaxy. You can see on the right, it's emitting light from stars. But then all of a sudden, you see this drop in the brightness, characteristic of a distant galaxy. And the reason for this is that the UV light of galaxies gets blocked out by clouds of hydrogen that intervene between the galaxy itself and the line of sight. So we talked about the epoch of reionization, where the universe is bathed in this hydrogen fog. That hydrogen fog blocks the UV light from that galaxy. And because we know exactly where that drop is supposed to occur, it's supposed to occur at 912 angstroms, any light that comes from the galaxy that is more energetic, so more in the UV than that particular wavelength, will get absorbed. So as the universe stretches, this characteristic drop will shift more and more to the right. And if you measure that difference between the 912 angstroms, or it's about 0.09 microns, you can see there's a big difference between 0.09 microns here on the graph and about 1 microns over here where this drop actually is. And that difference gives you the redshift. Now, to highlight this a little bit better, you can see the images that we would take with our telescopes over these three portions of the spectrum. And this is called the dropout technique. And you can see that if we look at the orange filter, so this would be an image taken with the James Webb Space Telescope, we would see the galaxy perfectly in the postage stamp on the bottom right because it's emitting light over there that is not getting absorbed. The same thing for the blue filter over here. You see the light being emitted and we see the galaxy clearly in the middle of the image. But then if you move to the pink filter over here, where it's not measuring any flux or any brightness from the galaxy drops out, so to speak, of this filter. And that's important because the location of this so-called drop tells you where this break is, this Lyman break, which gives you the redshift or the distance of the galaxy. So just to reiterate, if you look on the right, this is a nice sort of schematic. Let's say you have the galaxy at the top. If it's emitting blue UV light, that light then gets absorbed by the hydrogen cloud between the galaxy and ourselves. But if the galaxy is emitting redder light at infrared wavelengths, that goes through and we then capture that image. So it's quite important then to choose carefully which telescope you want to use to try and characterize your galaxy or determine the distance to it. The reason for that being is you have to carefully understand which physical process you are looking at from the galaxy electromagnetic spectrum, but equally you need to make sure that you are pointing in the correct at the correct wavelength where those physical processes are going to emit. So if we take the Hubble Space Telescope, for instance, to try and confirm the distances to these galaxies, the distance of a galaxy is a fundamental component to trying to characterize it. We might take Hubble. So if you remember the example just before where we had 3 different images, we now can use the full assortment of optical and infrared filters from the Hubble Space Telescope. So here you see an example spectrum of a distant galaxy. Right here, where the mouse is pointing, this is that 912 angstrom break, which you will see. So as the galaxy then gets redshifted further and further away from us, you can see that the hydrogen is absorbing this light from the galaxy and it's creating this break. And as it moves through these Hubble filters, these filters are what we use to take the images, you can see that in the corresponding images below, the galaxy drops out. And that again is important because the location of this dropout tells you an approximate redshift or distance, let's say. So now that we know how to search for distant galaxies, what sort of galaxies have we found? Which are the most distant galaxies that we know of? I like this picture quite a lot. I think this serves as a lot of inspiration for many astronomers. This is the Hubble Ultra Deep Field. So the Hubble Space Telescope is, or was, our premier flagship telescope. It was launched in the 1990s, and it's been taking these stunning images of the universe ever since for us. So in 2002, they installed the Advanced Camera for Surveys, ACS instrument, which is a visible optical instrument, let's say. And in 2004, they pointed at the sky and took an image for about 100 different hours, approximately. This was supposed to be a blank area of the sky, no larger than, if you take a pound coin and stretch it about an arm's length and look at the eye of the queen on that pound coin, it would be roughly that size area. It's a tiny area. And instead of revealing a blank sky with nothing in it, what it revealed actually was thousands and thousands of galaxies. And that's exactly what you're seeing here. Over here, there are virtually no stars whatsoever. What you're seeing are all galaxies, approximately 10,000 in this image. And if you use this so-called dropout technique, then looking at the different images taken with the Hubble Space Telescope over this area of the sky, a team revealed lots of different young galaxy candidates, which were extremely far away, approximately a few 100 million years after the Big Bang. And you can see that they only resemble these sort of blob-like objects. They don't appear to have very much structure. Again, the red is not what they look like intrinsically. This is just an artifact of how we image them. And you can see that there are quite a few of them, a lot more than one initially anticipated. However, again, these redshifts are only approximate values. They are approximate distances. What really we need is spectroscopy. So spectroscopy is the act of splitting up the light over a finer wavelength grid so that we can really identify signatures within a spectrum rather than over a coarse wavelength grid that is given by imaging capabilities. And what I mean by that is an example over here. So the top you have a galaxy spectrum, not at the redshifts we're talking about, of redshift 7 and above or so. This is roughly at redshifts of 2, which is still about half of the age of the universe or so. At the top, you can see these 2D spectra taken with the Keck telescopes on top of Mauna Kea in Hawaii. And these bright points correspond to emission lines. So we are no longer looking at this Lyman break, which covers a very coarse grid and this approximate distance, but now we are pinpointing the distances with these very characteristic features from gas within the galaxies, such as oxygen over here, or hydrogen, or nitrogen, or sulfur, for instance. So it's a much more precise technique to try and pinpoint the distance of a galaxy. However, as we mentioned, these galaxies are redshifted, so a lot of these features, when they're very, very distant, end up being outside of our telescope capabilities. One emission line, which still is visible from our telescopes on the ground, is called the Lyman alpha line. And that's what you see at the bottom here. This is a distant galaxy at a redshift of 6 approximately. So these distant galaxies that we're trying to look for at redshift 7 and above, generally speaking. And you can see this much finer grid of wavelengths if you want. The y-axis shows the brightness of the galaxy, the x-axis shows the wavelength. And again, you can see this characteristic drop that we were talking about, which we look at with imaging, but you can also see this larger peak over here. And this peak is emission that comes from hydrogen. This emission, generally speaking, however, is occulted by the hydrogen along the line of sight. It's absorbed. So for galaxies that reside within this hydrogen fog, we typically don't expect to see this line. However, it is one of the only lines that we can look for these ultra-distant galaxies because they are at such high redshifts, and we have to consider the capabilities of our telescopes. So it's a little bit like trying to look for car headlights in a fog from the US and Europe. It's not exactly easy, but this is what we try and do. So we set out to try and confirm the distances in this way with the Keck telescope about 5-ish years ago. We looked for the most distant galaxies we could possibly find at the time over what we call the Candles fields. The Candles fields are different portions of the sky taken with deep Hubble imaging. You can see them here at the bottom right. This schematic over here shows you the patches of the sky image with the Hubble Space Telescope, and their size is relative to the moon. So you can see it's a very small area of the sky, but they are especially deep images. So they're taken with very long exposures to try and find not just bright galaxies, but also very fainter galaxies. And so we used these fields and we tried to look for the most distant galaxies we could, and lo and behold, we found 4 galaxies using this so-called dropout technique, which suggested they would be at redshifts greater than 7. Greater than 7 corresponds to just a few 100 million years after the Big Bang. However, these only remain candidates as long as they haven't been confirmed with spectroscopy, with a spectrum, looking for that signature Lyman alpha line that comes from these star-forming galaxies. And lo and behold, we went out and we managed to find Lyman alpha, this small peak, as you can see here, in each of these 4 galaxies. These spectra over here correspond to each of these 4 galaxies. And at the time, 2 of these broke the distance records for galaxies at redshifts of 7.7 and 8.6. So these were the most distant galaxies that we knew of at the time. So 4 in total, about 5 hours or more of spectroscopy with Keck, and 4 out of 4 of these show this Lyman alpha line, which suggests that there's no more hydrogen around these galaxies blocking that UV light. We ended up taking this a little bit further. However, there was another galaxy called JD1. Unfortunately, we're not that inventive with names in astronomy. JD1 is a galaxy that we thought was at a redshift of 9 or so. You can see over here the postage stamps taken with the Hubble Space Telescope. Again, this dropout technique, if you look at the red circle, you can see that at infrared wavelengths, the galaxy is very clear, but then at optical wavelengths, the galaxy drops out. And it's because it drops out between this F105W and F125W, which corresponds to about 1.05 and 1.25 microns, that tells us that this characteristic break should be somewhere around here. But because the imaging filters are very broad, we don't know exactly where. So we then set out on an arduous journey to try and confirm the distance to this galaxy via spectroscopy. Myself and my two collaborators, Richard Ellis and Nicolas Laporte, at the time at University College London, we went to the Very Large Telescope in Chile, and we looked at this galaxy with more than 8 hours with some of the world's foremost telescopes, trying to look for this Lyman alpha line. And lo and behold, we found this line, as you can see on the left, this fairly clear line, which indicated a redshift of 9.1 or so, thereby confirming this galaxy as an ultra-distant galaxy. At the same time, our collaborators in Japan had used the ALMA telescope to look for a prominent oxygen line, which they found then on the right, suggesting that this galaxy was actually quite young, and not only that, but confirming the redshifts fairly precisely. So the oxygen suggests that some young stars are ionizing the oxygen around it. So at the time then, this was the most distant galaxy that we knew of, which we published this paper in 2018. However, that was not the end of this story in terms of confirming the most distant galaxies. Later on, in about 2009, the Hubble Ultra Deep Field Infrared was combined with the optical data from the Hubble Ultra Deep Field. So now we're combining infrared data from Hubble's flagship instrument, the Wide Field Camera 3, which is an infrared instrument, with the bluer wavelengths of the optical filters. And Hubble then, the team of observers combined all of this data to create this beautiful image over here called the Extreme Deep Field. Now, just like the Hubble Ultra Deep Field, there are virtually no stars in this image. There are about 5,000 galaxies or so, a lot of them very, very distant. And ultimately, this covers about 30 millionth of the whole sky. So it's a tiny, tiny portion of the entire sky. And this team then set out to look for these ultra distant galaxies, once again via this Lyman break technique, and ended up finding 4 of these galaxies. You can see them over here again. Like we saw before, they're these sort of little blobs, don't seem particularly interesting, but when you follow these up with spectroscopy, they are quite interesting. And this team did follow up the galaxy, this C component galaxy over here, which they thought was the best candidate for a ultra distant galaxy. And you can see a zoom in over here. It does not have a particularly imaginative name. GNZ11 suggests that this galaxy might be at a redshift of 10 or so. And the team went out then with the Hubble Space Telescope to get a spectrum, not just images, but a spectrum. And this is what they found. And you can see that it's, first thing you might take away from this image is that it's actually very, very challenging to get a spectrum of these sort of galaxies and to confirm their distances. However, this also might remind you of the spectrum that you saw before, where you see this characteristic break again. And this break over here tells you that this galaxy actually is at a redshift of 11. So this corresponds roughly about 400 million years after the Big Bang. We are now probing about 96% of cosmic time. So can we perhaps age date these galaxies? Now that we've confirmed that they are ultra distant galaxies, can we perhaps say something about them, about their properties? For instance, how old are their stars? The answer is in part. So if you look at the light distribution of a galaxy here in blue, you can see that this is matched by the brightness that's measured in the Hubble filters. And again, you can see this characteristic break. Now we know that this imaging is influenced by the intrinsic properties of the galaxies as well as the gas that resides around the galaxy itself. So the gas that resides around the galaxy itself gives rise to this characteristic drop. But at the same time, you might see that this point over here on the far right seems boosted relative to the others. That means that the galaxy is far brighter in this particular filter than it is in any of the others. These last two filters, by the way, come from the Spitzer Space Telescope. So here we're combining Hubble with Spitzer. So this tells us something about the underlying properties of the galaxies. And actually what this is telling us is that this galaxy has very intense nebular emission lines from oxygen. So it's saying that there are young stars there, prominent young stars that are ionizing the oxygen around us in a crazy fashion. And this is giving rise to this boosting of galaxy light in this particular filter. So we can try and estimate then the ages of these young stars via these lines. However, this is not the only source for this apparent boosting of the light in this filter compared to the others. Another one is what we call the Balmer break. So the Balmer break is another one of these drops in brightness that you can see over here. This is the spectrum of a galaxy at different ages, 20 million years, followed by 50 million years, 100, and 500 million years. And you can see that clearly as a function of age, this drop becomes much more prominent. So what's happening over here is that as a star gets older, the atmospheres of these stars are absorbing the metals that are here. And so that absorption of the light causes this dipping of the flux over here. And if we're to overplot, let's say, all of the points that you see on the left over here, you see that it gives actually more or less the same profile, the same shape. So one can ask then, if we take this distribution of light from the Hubble and Spitzer Space Telescopes, can we age date the galaxies? Can we age date the stars that are within these galaxies? So coming back to JD1, this galaxy that we had looked at with the VLT and with ALMA, now that we have a secure redshift, we can actually map out the underlying properties of that galaxy. And over here, you can see the total light profile in red. You can see this particular jump over here. And this jump can only be explained if you have this young component over here in blue, as well as this older component from more mature stars that are not just a few tens of millions of years old, but a few 100 million years old. And so we conducted a search for more galaxies like this. We found 3 of them. You can see similar sort of technique, similar analysis, and you can see that in each of these cases, you are seeing this jump between the last 2 points, and that jump can only be explained by the presence of more mature stars. But galaxies in general are expected to be quite young. They haven't had a ton of time to evolve in the early universe. So do we expect these more mature stars, or are these sort of flukes? Are they representative of the normal star-forming population or not? That remains to be seen. We can then ask ourselves, do the earliest galaxies already have supermassive black holes? In the local universe, we know that most galaxies host a supermassive black hole, and that this supermassive black hole evolves as a galaxy evolves as well, but it's unclear when they started to form. So the way that we can look for this again is with spectroscopy, where we try and find emission lines that cannot be ionized from the radiation of regular stars. They need something more potent, more powerful, like a supermassive black hole. And some of these lines include helium-2, for instance. So these are 2 examples over here, where you can see at the bottom, you see the yellow line. This is the signature of that helium-2 line. And at the top, you can see, sorry, I think my audio's changed. Can you still hear me? Sorry. So at the top.
Yes, we can still hear you.
So at the top of these 2 spectra, the spectra that are taken with the VLT and the Keck telescopes, that white dot is what corresponds to the emission line at the bottom. That indicates the presence of a supermassive black hole, probably. At the bottom here, you see another example. This is nitrogen-5, another line which is not easily excited by star-forming galaxies with just normal stars, but it needs some extra energetic input. So the presence of these 3 lines suggests that there might be some other contribution to ionize these lines other than just regular star-forming
sources, more likely supermassive black holes. Another question then that we can also ask is, do these galaxies harbor a lot of dust? So dust is expected to come from supernovae, which comes from the death of massive stars when they explode. Their enriched guts, so to speak, form and spread dust as well as heavy metals into the interstellar medium. And young galaxies are not expected necessarily to have copious amounts of dust, which is indicative of more of a mature system. But nonetheless, we set out with the ALMA telescope in Chile. That's what you can see at the bottom right over here, to try and look for this signature of dust. ALMA is a submillimeter telescope. You can see these arrays over here. It's characterized by these individual arrays, which work together to create one much more massive telescope. And that's what you can see at the top here. We did find dust in a very distant galaxy, a galaxy at a redshift of 8.4, corresponding to only about 4% of the present age of the universe. And you can see on the left this detection here in sort of white and green of dust. And if you overplot it with the Hubble image of the telescope here on the right, you can see that it matches up perfectly. The same thing happens with another galaxy at a redshift of 8 or so, and you can see the exact same here at the bottom, independently verified by a different team for another galaxy. So it seems like perhaps early galaxies have more dust than we initially expected. So is this more evidence for perhaps some sort of mature stellar population in these galaxies? It seems like it might. Another thing we can see is these galaxies, when we look at them in the local universe, appear to have this well-defined structure of spiral arms. But when we look at more distant galaxies, they appear to be just blobs. They don't appear to have much of a disk-like structure or any kind of rotation. They're more dominated by mergers, galaxies colliding together, this sort of thing. And if we take our telescopes and we point several times at different portions of the galaxy, we can get an emission line that looks like this on the right. You can see this peak. And that then tells us the redshift of the galaxy at different parts of it, essentially. And when we look at the differences in the position of those lines across the galaxy, we can see whether the stars or the gas in that galaxy is moving in some way. And for these galaxies, we might expect random motion, but we actually don't. So what you see over here, each pixel has a redshift measured, and if it's red, it's going away from us, whilst if it's blue, it's coming towards us. And you can see this very clear gradient in both of these cases, which suggests some clear rotation of the galaxy, not this kind of turbulent motion which you might expect if the galaxy didn't have a disk. And coming back to JD1, this very distant galaxy that has mature stars, you again see this gradient over here. So that begs the question, are galaxies all really, really young, or actually do they have some kind of structure? Are they really just small galaxies that are maybe a bit more massive? They also have young stars, but they also have older stars as well. They appear to have dust in them, which we wouldn't necessarily expect for very young galaxies. They also appear to have signatures of supermassive black holes and ultimately some disk structure as well. But we've sort of reached now the limit of what we can do with the Hubble Space Telescope and with spectroscopy from the ground. The reason for this is Hubble only probes up to about 1.6 microns in its imaging capabilities, and distant galaxies emit the majority of their light and the majority of signatures from their stars and their gas at even longer wavelengths in what we call the rest frame optical. So Hubble can't probe galaxies further than it currently is at redshifts of 10 or so. On the ground, if we try and get spectroscopy with infrared telescopes, we only probe up to about 1 to 2 microns or so, but we are affected strongly by the atmosphere of the Earth, which is blocking a lot of the infrared light. So there is a need then for space-based spectroscopy in the infrared. And lo and behold, then that is where the James Webb Space Telescope then comes into play. So the James Webb Space Telescope is a much larger telescope than the Hubble Space Telescope, created with 18 different mirror segments, as you can see in this little movie over here. The mirror segments are protected by a 5-layered heat shield. The James Webb Space Telescope, because it looks in the infrared wavelengths, has to be protected by all sources of infrared radiation, including from the sun and including from the Earth, because if you're trying to look for extremely distant sources in the early universe in the infrared, even small bits of infrared light that hit the mirror could be interpreted as a distant galaxy. Since the Webb is such a big telescope, it was folded up, as you can see here in this little schematic, and it was fit then at the top of an Ariane 5 rocket. This is a European rocket, and it blasted off then on Christmas last year, where it then started its one-day journey up to what we call Lagrange point 2, this point in space where the orbits of the planet create an essentially neutral gravitational pull, and the telescope during its month-long journey to that point unfolded into what you can see here in the video, and then began its 6-month long commissioning to try and make sure that everything had aligned properly, everything had unfolded properly, and all of the instruments were working optimally. So you can see here just a nice illustration of just how much bigger the James Webb Space Telescope is compared to the Hubble Space Telescope. It has a mirror that is about 6.5 meters in diameter compared to Hubble's 2.4. And this is crucial because it allows for about 6 times more collecting area to collect these infrared photons. It has 4 different primary instruments over here, of which we can use for both spectroscopy in the infrared as well as imaging in the infrared. So to list these 4 over here, you can see NIRCam here in the middle, where you see these sort of 2 larger segments which are divided in 4. This is the flagship imager, let's say, in the infrared wavelength bands from James Webb. It extends what Hubble is able to see out to about 4.4 microns. Then we have NIRSpec on the left over here. Again, 4 different quadrants, but this is primarily a multi-object spectrograph, where inside each of these quadrants, we can put quite a lot of galaxies, hundreds of galaxies, and take a spectrum out from anywhere between about 0.6 to 5 microns, thereby getting the full rest frame UV and most of the rest frame optical of distant galaxies. We also have NIRIS over here. NIRIS is a slitless spectrograph and imager. And what this means is you don't position the spectrograph on a particular galaxy. You point it at a particular point in space, and you end up getting a spectrum for each object that is in that field of view. The last one over here is MIRI. MIRI is a far infrared imager and low resolution spectrograph. It can do these, it can take images and take spectroscopy out from about 5 microns to 25 microns. So it's really extending everything that we've been able to do so far with Hubble and with our ground-based telescopes like Keck and the VLT, for instance. And so this is a nice illustration, I think, what we're able to get now with the James Webb Space Telescope, since it probes these much needed infrared regions. So this is an example spectrum of a very distant galaxy, a galaxy at about redshift 7.5 or so. And all of a sudden, all of these features here, which we couldn't access before, are now available to us. So we can get information about ionized bubbles, so whether the galaxy has ionized its immediate surroundings via this Lyman alpha line and the Lyman break, which you can see over here. We can also get information whether this galaxy has supermassive black holes in the middle from these high excitation lines like helium-2 and nitrogen-5. We can get the star formation rates of the galaxies via this sort of empty portion of the spectrum, number of ionizing photons, the stellar ages of these galaxies over here, whether the galaxies harbor heavy metals or not, and also the stellar masses of these galaxies. So I was fortunate enough to be at the launch of the James Webb Space Telescope, and on the day you go out onto this platform, this sort of rainy gray day, hoping that the launch isn't going to be scrapped, and then you wait 3 seconds for that countdown, and after 3 seconds you see this great big ball of flame emerge from the horizon. You tend to experience a little bit of a roller coaster of emotions. For many, this is a lifetime of work and dedication, so the sense of joy and sort of relief and nervousness, even fear to a certain degree, are all very palpable. And the launch only really lasts a few seconds, in what we can see, but the rumble, of the Ariane 5 rockets really continues for minutes until, even after the telescope or the rocket has cleared the clouds. And once the James Webb then arrived at its destination and started taking images, it revealed images that we could only dream of. This is an image taken, a test exposure taken with the James Webb Fine Guidance Sensor, so the instrument that it uses to make sure it's pointing at the right area of the sky. And it became instantly, after, I think this was a 32-hour exposure, one of the sharpest and one of the deepest infrared images taken at the time. And again, you can see there are a few stars over here, but primarily what you see is this sea of galaxies in the background, of which no doubt there will be some extremely distant galaxies. And just to highlight quite starkly, I think, how the resolution of the spatial resolution of Hubble's capabilities has already revolutionized, of the James Webb Space Telescope, has already revolutionized what we can see. On here, at the bottom, you can see a comparison between our previous telescopes and James Webb. MIRI on the right, you have Spitzer in the middle, and on the left, you have the WISE telescope. And you can see how on the left, you see a few of the brightest sources, but there's insufficient resolution to look for anything over there. But then James Webb, you get a whole lot more detail. So on July 11th, the first science grade images were revealed, the Webb's first deep field, and this image was truly stunning. About 12.5 hours of near-cam imaging over a galaxy cluster over here. You can see these so-called Einstein rings, which is essentially background galaxies which are being stretched and amplified due to the strong gravitational pull of these galaxies here in the middle. And not only did James Webb look with near-cam, it also looked with near-spec, and this highlights exactly what I was trying to showcase beforehand, where all of a sudden we now don't rely just on this Lyman alpha line at about 1 micron or so to confirm the distance of these ultra-distant galaxies, but now we're all of a sudden getting oxygen, hydrogen, even neon, and all of these now serve as indicators to confirm the redshifts or the distances to these galaxies and tell us something about their ages as well as the metallicity, and a plethora of other things. And just to show you a comparison, this is one of the best spectra we have of a redshift 8 galaxy, so the same redshift as this particular galaxy here. And you can see the difference both in quality and in terms of indicators that we get. So James Webb is already blowing things out of the water. So I am part of the Through the Looking Glass JWST ERS program. This program will be taking the very first and the deepest extragalactic data of the entire ERS campaign. The idea is to target another galaxy cluster, which you can see here on the left with nearest and near-spec spectroscopy, as well as near-cam imaging of a blank field that's offset from this galaxy center. And we take advantage of this effect called galaxy lensing, where we're able to spot ultra-distant galaxies that are a bit fainter. This is the data that we got. So on the left, you can see the nearest image where everything within the field of view, we get a spectrum. And on the right, we see the near-cam 7-band image compressed together. So we have 3 different images across wavelengths, which we've combined here on the left, and then 7 different bands for near-cam over here on the right. So with 13 hours of nearest, we already confirmed 2 of the most distant galaxies that we currently know of. You can see this characteristic Lyman break once more. Now it's not shown with imaging, but it's shown with spectra. You can see these spectra here at the top, and then at the bottom you see the 1D spectrum, and you clearly see that break, and that break once again tells you the redshift or the distance to the galaxies. And at the same time, we then did a first search for the most distant galaxies we could see, and we found these two here at the top. Well, we found 5 other ones which are at the redshifts of 9 to 10, and then these other 2 which were at redshifts greater than 10 or so, and you can again clearly see this break. But crucially, I'm highlighting here the filters that overlap with Hubble. And if you look at this one on the right, you see if we image this with Hubble, we wouldn't see anything. GLASS is not the only ERS program which was recently taken. The SEERS survey was also taken recently. Again, a multi-band survey with the NIRCam instruments on board the James Webb Space Telescope over a field that was previously known with Hubble, previously imaged with Hubble. Again, this is 7 different bands, and you can see the mosaic over here plotted throughout the screen. Researchers, including ourselves, had a look at this data and tried to look for the most distant galaxies we could. And collaborators or the PIs of SEERS found this galaxy at a redshift of 14.3. This instantly breaks the record that we previously had at a redshift of 11 or so. You can see this dropout nature over here. The imaging is represented as the circles here, and our best fit model of the galaxy as these lines. And you can see that it appears fairly convincing. And then only a few days later, another galaxy that apparently broke the distance record again at a redshift of 16.6. So we're only looking at a few 100 million years after the Big Bang now. And again, you can see that characteristic break and dropout feature. But do we expect so many distant galaxies? Our theory suggests perhaps not. So over here, on the y-axis, you see the density of sources. On the x-axis, you see the redshift. And as you can see, as you go to higher and higher redshift, you get less and less sources. And over here, our most distant known sources with Hubble seem to end at a redshift of 10 or so, suggesting that there's not really much. But James Webb is now pushing this frontier out to redshifts 12, 13, and nearly 17, suggesting perhaps that star formation actually started at earlier times and not at later times. However, all of these need to be verified with spectroscopy. They remain galaxy candidates for the moment until we can confirm them with spectroscopy. And so one such programs that will be doing so is my own one with James Webb, where we'll be targeting 10 distant galaxies for about 25 hours with NIRSpec. So we'll be getting spectra from 0.6 microns all the way out to 5 microns, and we'll be able to detect all of these features that I showed you before, including these strong emission lines, in only about an hour of observations. This is the NIRSpec setup. So the galaxies will be placed in here where you can get a spectrum for each of the little slits that are in these quadrants. And this is the sort of spectrum that we expect to get, the 2D at the top. And if you collapse that, you get this beautiful spectrum here with all these features. So I think I'm going to end it over here. My main takeaway messages is that the ground and space-based facilities that we've had up until now have really pushed the frontier of early galaxy evolution. We've discovered objects all the way out to a redshift of 11 or so. We've constrained their distances, their masses, and their star formation rates. And whilst in theory we would expect these galaxies to be very young and pristine and largely invisible to UV imaging and spectroscopy, analyses with Keck and the VLT, for instance, suggest that actually these galaxies might be more massive, more dusty than previously thought, and also formed earlier than previously thought. And lastly, the arrival of James Webb is now offering unprecedented imaging and spectroscopic capabilities, showing us images and spectra and information about galaxies that we could have only dreamed of up until now. So I'll end it there. Thank you for your time.
And thank you, Guido. This is intense look at not only what we have previously discovered about this, but a sneak peek at what we are currently discovering about these very early galaxies. The idea that we could push to redshift 16.5 is totally unprecedented. Not something that I got in that idea was not anywhere near in my head when we were doing my graduate work well, a few decades ago. So you must be pleased with the progress we're making there.
It's wonderful. I think none of us, we all expected to be surprised in some shape or form, but I don't think anyone expected to be surprised to this extent or this quickly. We've only had James Webb for about a month and a half or so, nearly 2 months. It's already broken the distance record several times, and it's already revealing the physics of these early galaxies in exquisite detail that we could have only, or that people have been dreaming about for 10 to 20 years.
Okay, well, one of our viewers on YouTube was wondering, okay, well, you said Hubble had a limit around 10, 11 that it could go out to. If there were galaxies beyond these 14 and 16, just how far could Webb go if there are galaxies to observe at those redshifts? Can it get to 18, 20? Is there a limit?
In theory, yeah, it can get to 18, 20. In fact, there are some results out there who are suggesting that there might be a couple of galaxies out at redshift 20. This has to be verified and peer reviewed. But there are people looking out as far as redshifts of 20. Of course, you pointed out a really valid point, though, I think, which is, we don't know whether they even exist. So right. Our models are a little doubtful, let's say, of finding galaxies that far out. But if they do exist, then in theory, James Webb should be able to find them. The only thing is that we wouldn't be able to look for the most, we'd only be able to look for the brightest such sources, because the faint ones would still be out of, I think, James Webb's capabilities. We'd have to be looking at the sky for a very, very long time.
Right. And that's another thing to point out to folks is that, what are we calling galaxies here? I mean, these are sort of proto-galaxies, right? I mean, what is the masses? Are we getting down to 10 to the 8th solar masses type range, or what? How large? Because they're certainly not the size. They're not Milky Way sized galaxies. They're not even dwarf. They're not even the large dwarfs that we know of in the local universe. What masses are we really looking at when we're talking about these very, very?
So that's something we're actually able to look at now for more or less the first time. Most of the mass of these galaxies is contained within the rest frame optical, which up until now we could only see with 2 bands with Spitzer, but these bands were heavily contaminated by emission lines and features which skewed, let's say, our results. With James Webb, we're able to do this more efficiently. And people are finding that these galaxies are more massive than we thought, 10 to the 9, 10 to the 10 even in some cases.
Really? So we're getting to 1 billion solar masses, and that is just in baryons, or is that baryons and dark matter?
That's just baryons. That's just baryons.
Okay. All right. Wait, for the audience, baryons is the normal matter, the hydrogen and helium and stuff. It's amongst cosmologists, baryons is just what we use as our code word for that sort of stuff. Got to make sure that our public audience recognizes those jargon words.
Yeah, absolutely. I mean, the regular matter we can see with James Webb. Dark matter we would have to constrain indirectly through gravitational effects. We can't see that directly. And so here we're talking normal matter, let's say, the stars and gas. And in some cases, we seem to be seeing galaxies that are more massive than previously thought. We already looked at this a little bit with Spitzer and ALMA, this JD1 galaxy, for instance, which is supposed to be a lot older and a lot more massive than previously thought. But James Webb is really taking this to another level. The only caveat I will add to this in terms of these distant galaxies is we know how to search for distant galaxies and characterize them reasonably well. What we don't know very well yet is how the instruments of James Webb behave. And so a very important component of all of this is essentially learning on the fly how these instruments respond and making sure that they respond in a way that we understand. And so what we then interpret of these galaxies is accurate. And that will take a little bit of time still.
Exactly. Experience. I mean, I remember several times in Hubble's history that we've had to recalibrate, go back through and do recalibrations of all the data sets in the archive, just because we've learned more about how the instruments are responding. So even if we have fantastic observations, fantastic results right now, they have to be taken with a grain of salt until we have the experience with Webb's instruments to really validate them.
That's right. But part of the excitement of James Webb is also, getting surprised. It's we expect our results to be extended to a certain extent. We always expect to find more distant galaxies, I think, but part of the enjoyment of all of this is really being surprised in ways which we didn't really imagine. And that forces us then to rethink, perhaps some of our models or our techniques and rethink what we know. And that's a wonderful part of astronomy and science in general, I think.
Wonderful. Yeah, I will definitely say that, 14 and 16 right in the first month is definitely qualifies as a surprise. All right, there was one other question I saw that I wanted to ask you, and it's trying to relate the local universe to the distant universe. And so they asked a question that I translated into two different questions. One, are galaxies being formed today? And are they similar to these very early galaxies? I presume sort of saying, hey, if what we see in the local universe similar to what we're seeing in the distant universe, just at much, much greater distance?
That's a very good question. Yes is the answer. We have there are galaxies forming today, and there are galaxies also that look very similar to what we see in the distant universe. Obviously, everything we look at is, a snapshot of the past in a way. We can't see this in real time, but this is actually a very big part of studies of the early universe. Because these faraway galaxies are so difficult to find and confirm, we often look at the local universe, looking for what we call lower redshift analogs of high redshift galaxies. So galaxies in the local universe that we think resemble very distant galaxies, to try and understand more about the properties and conditions of those galaxies. So yes and yes is the answer to that, I think.
And I guess I would think that there is a significant difference between them in that these galaxies we're seeing in the very early universe, if they're forming so quickly, they're going to continue to form and probably end up as, giant elliptical galaxies. Whereas the ones in the local universe are going to be these dwarf small galaxies, and they're never going to get to be the giant ellipticals. I mean, the things that form first are the highest density peaks of the density distribution. So there's that small difference I've always kept in my head. Is that reasonable?
Yeah, I think that's definitely reasonable. Obviously, we don't, in our lifetimes, we won't know how these currently forming galaxies are going to evolve. But I think one thing that's important to consider, of course, when doing these studies is, it is very well and good to compare these galaxies across cosmic time, but we should keep in mind that the conditions of the universe have changed, across 13 billion years. So the conditions in which the first galaxies formed are different to the conditions in which the galaxies today are forming. Nonetheless, if you compare apples to apples in terms of specific properties, that I think one can do. But for sure, the conditions around those galaxies has changed, and no doubt that would have some sort of impact on the structure, the large-scale structures of galaxies, at least.
Right. Okay. Well, Grant Justice has been paying attention to the questions in the chat. Grant, why don't you turn on your video and welcome, and tell us what questions you found in the chat.
Sure, absolutely. Actually, following up kind of from the last one, in your observations, have you found that early galaxies tend to have larger or smaller stars compared to recently formed one? Is there any correlation?
So we don't have the resolution to look at individual stars in these distant galaxies. Galaxies that are closer by, we can see clusters of galaxies, but we don't quite have the resolution to look at stars, individual stars outside of our own galaxy. What we can do, though, is we can compare the sizes of galaxies themselves, or we can try and estimate the ages of the stars within. And we do find that some of these distant galaxies have older stars. The stars that we see today are much, much older because galaxies have had a lot more time to evolve than those early ones. But if you compare, for instance, with these so-called local analogs, then we can see some similar traits across the two different populations. But we don't have the resolution, even with James Webb, to image individual stars in these distant galaxies.
Okay, so that brings up a side question that you mentioned a bit in your talk, that we got the redshift for a galaxy to know what redshift we're seeing it at, and then we can age date, that you've got some stars within them that are like a few 100 million years old. So are we getting a good estimate for when the first stars in the universe formed? How close to the Big Bang we're getting there?
That's an excellent question. So when we get the light from the galaxies, we're seeing them as they were then. And if we can measure the age of those stars then, what we can do is rewind the clock. And the way we do this essentially is we recreate the history of how this galaxy formed those stars by trying to match the light profile. But and we do this with models of galaxies, but this is an extremely uncertain practice. It's the only way we can do things for the moment in the absence of spectroscopy. It was the only way to do it. So you can pinpoint then a time at which these galaxies were born, or these stars were born, but it'll still have a very large error bar. It's very uncertain. What you need is spectroscopy to be able to look at this so-called Balmer break again, this jump that you see, which is due to those mature stars. And if you can directly measure that jump, you'll have a much better handle on the ages of those stars than just from imaging alone. Okay.
But it does sound like we're finding that, the first stars are forming within 500 million years after the Big Bang.
Yeah, so we know
getting it exact is going to be something to look forward to.
That's right. We know at this point in time now, just due to distances alone. I mean, confirming distances to early galaxies is the most direct way to essentially figure out when the first stars and galaxies formed. And that alone is telling us that the first stars and galaxies probably formed within the first 200 to 400 million years after the Big Bang or so. Roughly 96-97% of the universe's present age.
All right. Grant, what else we got?
I actually love this one. We're gonna pull back the curtain a little bit. Is it common to incorrectly date such early distant galaxies? It's nothing short of incredible that we're able to date them at all.
That's a great question. The answer is probably, but we don't know until we actually confirm those, the dates of these galaxies. There's a very large error bar on these estimates. So whether we've pinpointed the exact age or not remains to be seen, but there's a very gray area there, let's say, a big margin for error.
But don't sell yourself short, because the error bars have been decreasing from being really huge. Now you're just saying, okay, they're here, and they really want them to be here. But you're doing fantastic.
Absolutely. Thank you. I mean, these telescopes really are allowing us to push the frontier of what we can do. I mean, it is marvelous that we're even able to attempt this sort of thing. But ultimately, getting sort of direct confirmation is what we want to do. But that's extremely challenging. One of the things that people have been wanting to do for a long time is the detection and confirmation of what we call population 3 stars. These first generation of stars, they're the very first ones that formed from pristine hydrogen gas. They don't have any heavy metals like carbon or oxygen in them, and those are the ones that we know were the very first ones to form. And direct detection is much clearer, let's say, than rewinding the clock as such. But for the moment, it's the only thing we really can do.
Right. And for those pop 3 stars, it's, I've seen different arguments as to how quickly those might form once after ionization.
That's right.
After recombination, sorry. Okay, Grant, what next?
Thank you. Do indications of dust in these deeply redshifted galaxies upset prediction models of early star formation?
Again, a good question. Yes, to a certain extent. For a very long time, the assumption with these galaxies was that they didn't have any dust at all. In fact, in a lot of our analyses and our models, dust was never included, which has a significant impact then on how we interpret the data, because dust, in effect, shields a lot of the light from young stars. So, for instance, if there's a lot of dust in these young galaxies, we might be undercounting the number of stars that they're forming. And that's really important for our models of early galaxy evolution. So we hadn't been including that because we assumed there was no stars. There was no dust, sorry. ALMA has really been revolutionizing this picture in the sense that it's an extremely sensitive telescope in the sub-millimeter range of wavelengths, and that is where galaxies tend to emit light from dust. So the dust gets heated up, it absorbs UV light and then re-emits it at infrared wavelengths, or sub-millimeter wavelengths rather. And ALMA is finding in these very distant galaxies that there seems to be a fair amount of dust. And so what we need to do now is look back on our theory on how this dust is produced in terms of supernovae or not, and whether those supernovae come from these massive stars or not. So yes, it is upsetting a little bit, let's say, our original theories, but that's great. It means we still have a lot to learn.
Yes, I always like to say when you uncover something you didn't expect, it just shows you've got another project to pursue to understand that result. And we love being ignorant because that gives us more to understand about the universe.
Absolutely.
All right.
So given that you have so much more available to you coming up now with JWST, we've spoken a little bit about the instruments and like becoming familiar with them, but what are you most excited for, like technique-wise, for dating early objects or exploring a little further into your specialty?
That might be my favorite question, I think, so far, purely because I think the nice thing about James Webb now and having these capabilities, which we could only dream about for a long time, is it's no longer, the frontier is no longer just extending what we've done so far. The frontier now, I think, is becoming creative with the capabilities that we have, and learning how to combine the data from these various instruments in terms of trying to understand what we see. And when we combine, these different indicators, for instance, what does that tell us about galaxy evolution? So it's the unexpected, let's say, and the unknown, which I think is really interesting. And I think the challenge really now is to get creative with the instruments and the data sets. And this is something that we're trying to do with the GLASS CRS program in terms of, looking at this galaxy cluster, not just with the nearest instrument, which is going to give us, or which has given us a spectra of everything in the field of view, but also then following it up at different wavelengths with the near spec instruments, so that we can directly compare different wavelengths and different instruments and see how to best optimize them to learn as much as we can about these distant objects.
Yeah, and you had a great point about using observations with ALMA, right? And getting into the millimeter and the radio waves, which have very fine resolution as well.
That's right.
Hubble and Webb are the kings of the sky of the space telescopes in getting the resolution, but going to the millimeter and radio wavelengths, where you can get these big arrays to have the really fine resolution, I'm sure you'll be able to figure out some cool ways to involve them into adding more to the information that you get to sort and to find out the
Absolutely.
answers.
So there's already, this James Webb ALMA synergy is something that everybody is really looking forward to, because ALMA probes physical mechanisms and frequencies or wavelengths that James Webb does not probe. And so, one example, for instance, of how, or two examples, let's say, of how we want to use this synergy is, let's say, the confirmation, for instance, of redshifts or distances. As an example, if we get a so-called dropout galaxy, like I showed with James Webb, which does not show, we do not have spectroscopy for that. One avenue is possibly we can try and get a spectrum of Lyman alpha, which might not show because it might be absorbed by the intervening hydrogen at that epoch. So we might look for emission lines with ALMA, which looks for oxygen traces, for instance, like I had shown before. And that oxygen is not affected by the surrounding medium of those galaxies. So James Webb would find these distant candidates. ALMA might confirm them. Another one, again, is dust. ALMA really probes the dusts that James Webb cannot. And so trying to maximize the synergy between the two telescopes to try and understand where this dust is coming from and how much is there is really, really important.
All right. I think we're going to let you have one more question. So Grant, find a good one to end with here, because
All right.
We've gone on long enough here.
That's fair. I'm noticing an ongoing theme to these questions as well. So you did mention that you had some, obviously we've always had some issues observing and quantifying dark matter, but you said some dwarf galaxies appear to have little or no dark matter associated based on observations so far. Do you find this to be a theme with early galaxies that you observe?
That's a good question. This isn't something that we've explored with James Webb yet, not directly at least. The one thing I'll say with that is if we compare, so the standard assumption is that galaxies form within halos of dark matter, that the dark matter and the evolution of the dark matter halo and of the galaxy itself, this so-called regular matter, is linked together. And our models and our observations with Hubble appear to agree. However, this age dating, let's say, of the stars and the fact that we're finding now a lot more distant galaxies with James Webb does not agree with our models of the evolution of dark matter halos. So it suggests that there could be something we don't understand, some apparent decoupling, let's say. So that's where the uncertainty sort of arises. We don't know if our models of dark matter perhaps are missing something. It's entirely possible we're missing something, or else, maybe we're looking at a particular patch of the sky which seems to have a lot of distant galaxies that isn't representative, or something's gone wrong. We don't know, or it's great that we have this to figure out. But in terms of these dwarf galaxies, which you mentioned, we have not done this sort of analysis with these ultra distant galaxies. That's not something we've looked at directly, only on a statistical level.
Right.
Not
and as we assemble all these observations and do multiple fields and everything, as the statistics are going to get larger and larger, and we'll be able to tell, are we looking at special regions, are we not? We're seeing a lot of galaxies. All I can say is that that makes it very exciting. And so I do not expect it to fit with what I was taught in graduate school at all. All right.
But it's wonderful that we're learning new things. That's what's great about it.
That is science, right? If we didn't learn new things, we wouldn't be doing our job.
That's right.
So after Webb's been up for a bit, we'll have to have part 2. Is what you're saying.
Most definitely. This is not the last we're going to hear from Guido on this subject.
That's right. Our next data set will be arriving end of October or November. So stay tuned.
All right. Until such time, you all should stay tuned. Next month on October 4th, the universe of Dante Alighieri. Please join us. Until that time, please keep exploring your universe. Take care.